Well, hello, pre-calculus class. Well, here we are for our third and final lesson for this week. I think this should be Friday for you guys. We're going to be looking at one more section together, talking about vectors, but this time vectors in 3 dimensions. We're going to be looking at vectors in space, 6.3. So first of all, you guys are familiar with the XY coordinate plane. All we're doing now is adding the z-axis as well. And this is showing the standard way that we show this. We usually show z as going vertically up and down, and then the y-axis as pointing off to our right, and the x-axis is pointing slightly off to our left. So this is the standard orientation for that. And you can kind of see here we've got the YZ plane is the plane that sits with the YZ, being parallel with YZ. You have the XY plane, and you have the XZ plane. All of those 3 planes. Some people like to remember the way this looks by using what they call the right-hand rule, where your thumb goes in the direction of Z, and then your fingers curve around from the x-axis towards the y-axis. So if that's helpful to you, that's kind of standard positioning of how they show 3 dimensions. Also then can split all of these quadrants into 1, 2, 3, 4, 5, 6, 7, 8. We've got, or octants, I guess. There's 8 different areas or regions of space that are then divided by this coordinate plane. Remember, we were familiar with the 1, 2, 3, and 4 from the XY plane, so it just becomes 1 through 8 when we're talking about the areas of space. Okay, so just to get some quick, easy, I think, review practice here, if we're going to plot a point in 3 dimensions, and the point is 3, 4, 5, all we do is, again, remember, these are going to be always in the order of x, comma, y, comma, z. Well, we just need to travel out 3 along the x-axis, then along 4 in the y direction, and then up 5 in the z direction, and then put our point there, which would be 3, 4, 5. So notice that we're just traveling along each of those dimensions. I do think for this reason it's always easiest to start with the x, because that's the one that's kind of on an angle, and then the y and the z are all on straight lines, both horizontal and vertical lines. If it helps you to visualize a box being formed with one point being of the box at the origin, and the other point, the vertex of the opposite point being on the where the point is, then you can show it this way if that's helpful to see this in 3 dimensions. Sometimes some students have a little bit of difficulty seeing this 3D, but if that box helps you do it, you can draw the box in. Okay, so why don't you guys work on this one? Try to do this one. Negative 3, 5, -1. So what are we going to do first? We'll go 3 in the x direction to here. Then we're going to go 5 in the y direction, this direction. And then we'll go -1 in the z direction. And then we make our point, and this will be point P. Again, if it's helpful to you, you can also then draw in the box. Try my best to do this in a dotted fashion. Anyway, looks something kind of like that. It's not perfect, but kind of shows you this would be one vertex in the box, and the opposite vertex would be over here in this corner. So that'd be the point P. How about this one? 4, -2, -2. Well, again, we would go 4 in the x direction positive, so 1, 2, 3, 4. Then we go -2 in the y direction, so we'd go 1, 2 over to here. And then we go 2 down, 1, 2. And this would be our point P on this one. So here's the 3D distance and midpoint formulas. So given 2 points in space where P is x1, y1, z1, and Q is x2, y2, z2, the distance PQ is just the distance of Q2 minus Q1 squared plus the subtraction of y1 from y2, and then z1 from z2 squared. So you add all of that together, you take the square root, just like you would have done in 2 dimensions, you just have the third dimension that's there. Obviously, midpoint formula is the same as what you're already used to. Again, just adding the z dimension. But otherwise, it's the exact same thing you already know. So if I was to ask, find the length and the midpoint of the segment from A, which is 3, 0, -2, to B, which is -1, -4, 6, we could do that. We would just take the square root of the difference of, or the square of the difference of each of those values. So we plug in, remember these are our 2 values and these are our 1 values. So you would just make sure that you always start with the second point, right? Because if we had a vector, the second point is where the arrow is pointing to. So we start with that point and we subtract off the tail. So -1 minus 3 squared, -4 minus 0 squared, 6 minus a minus 2 squared. And when you do all of that math, you get the square root of 96, which also can be rewritten as 4 square roots of 6, or about 9.8. Now, if we're doing midpoint, we just add the 2 together, divide by 2 for each x, y, and z. And again, you can do this simple math, and it'd be 1, -2, 2 would be the midpoint. Okay, so the vector AB from A to B is expressed in component form as v1, v2, v3. Notice here that we've just added now the third subscript for v here, because now we have not only an x and a y, but also a z coordinate. And again, we get each of those just by subtracting the first point from the second point. So x2 minus x1, y2 minus y1, z2 minus z1. And then we can get the magnitude of the vector, remember, which is a scalar quantity, just the measurement of its length, by taking the square root of the sum of the squares of each of those components, x, y, and z. And then we can take our original vector and we can divide it by the magnitude of the vector in order to get the unit vector, right? To get a vector that is exactly 1 unit long in the direction of the vector, the original vector. So given points A and B, express vector AB in component form. Well, we would just subtract A from B, right? So we take 3 minus 5, 6 minus 1, 2 minus a -1. And we get -2, 5, 3. If we wanted to then plot that, we would just go -2 in the x direction, 5 in the y direction, 3 in the z direction. These were the 2 original points that we were given, point A and point B. Notice that the line would just connect from A to B like this. And the vector that we just discovered is just repositioning that exact same vector at the origin. That's what the -2, 5, 3 is. So find the length of vector V, which is -2, 5, 3. Well, we find the length by just taking the square root of the square of each of those numbers, which have been added together underneath the square root. So -2 squared plus 5 squared plus 3 squared. So 4 plus 25 plus 9 is 38. Square root of 38 is roughly 6.16. Now, if we're to find a unit vector in the direction of vector AB, all we do is we divide the vector itself by the magnitude of the vector. And that will give us ultimately a vector of only 1 unit long in the direction of vector AB. So we just divide it by that 1 over the square root of 38. We multiply by 1 over the square root of 38. So that just goes in there. And then we can rationalize the denominator by multiplying both of those by the square root of 38 over the square root of 38, which leaves us with a 38 in the bottom and the square root of 38 on the top. All right, so vectors in space. If we let k be a scalar and we have the vector v and w, and theta is the angle between v and w, here's a few properties that your book walks you through. The vector v is equal to the vector w if and only if v1 equals w1, v2 equals w2, and v3 equals w3. In other words, the x, y, and z components of each vector must equal one another if the vectors are going to be equal to one another. That makes sense. If we're going to be adding vector v and w together, then we just add the x components of both of them. We add the y components of both of them. We add the z components of both of them, which are represented here as v1 and w1, v2, w2, v3, and w3 respectively. If we're going to do scalar multiplication, we just take that k and we multiply it into each of, again, the x, y, and z components of the vector. Just distribute it in. For vector subtraction, remember, it's the same thing as adding the negative of the vector. So if we're going to subtract vector w from vector v, we just add the negative of the vector to it. The zero vector is obviously just 0, 0, 0. And the dot product works just as we had before with 2 dimensions dot product. All you do is you take the magnitude of vector v times the magnitude of vector w, and then you multiply it by the cosine of the angle that is formed between the 2 vectors when they're put in standard position at the origin. So we multiply by cosine of theta, the theta being the degree measurement between the 2 vectors. Another way that we can write that is also just multiplying the x components of the vectors together, and then adding that to the multiplication of the y components, and adding that to the multiplication of the z components. This would be the x, y, and z components of those vectors. So we just multiply the x's together, multiply the y's together, multiply the z's together, and then add them all together. So let's get some practice doing all of those operations. So use for point P -5, 2, 0, and Q is 1, -3, 2, or -2, to complete each vector operation. So the first one tells us to do 2P plus Q. So we're going to multiply 2, first of all, in through the first vector, and then we're going to add them both together. So when we multiply 2 in, we get -10, 4, and 0, and then we just add these together. And we're left with the answer of -9, 1, -2. So -10 plus 1 is -9, 4 minus 3 is 1, 0 minus 2 is a -2. And you're done. What about this one? 1/2 r minus 3q given q and r up here above. Well, again, we're just going to multiply that 1/2 into each component for r, and then we're going to multiply this -3 into each component of q. So we do that first, and we get 3, 2, -3/2, and we get -3, 9, and 6, and now we just add them together. And we get in the end 0, 11, 9/2. Okay, here's just another couple examples. You can pause the video here, guys, if you want to, and see if you can get the same answer that I do. Given that P is -8, 2.5, and 3, and Q is 4, 0, and -7, find -1/2 P plus 3Q, and then P minus 4Q. So why don't you pause it right now and see if you can get the correct answers. All right, and so if you did that work, you should have gotten something that looks like this. And your final answer would be 16, -1.25, and -22.5. And for the other guy, you should have gotten -24, 2.5, and 31. Again, you can check your answers here, but that's what you should have gotten in the end. All right, so as I said before, the dot product in 2 dimensions, remember, was just the magnitude of v times the magnitude of w times the cosine of the angle between them. Also be rewritten as v1 w1 plus v2 w2. If you know the components, this would be the x components, these would be the y components. In 3 dimensions, it's the exact same thing. If we know the magnitude of both of the vectors, you just multiply them by each other and then multiply them by the cosine of the angle between them. But remember, in 3 dimensions, another way of doing that would just be to do the components. But now we have an x, y, and z component. So we have to multiply the x's together, multiply the y's together, multiply the z's together, and then add them all together. Now remember, this becomes important because if we know, for example, the x, y, and z components, and then therefore we can know the magnitudes of them, we can also use this to find theta, find the angle in between the 2 vectors. So use Q and R to complete each vector operation. So first of all, if we're going to find the dot product of Q and R, remember, all we're going to do is multiply the x's together, multiply the y's together, and multiply the z's together, and then add them all together. So to do this, we just do 1 times 6, We do negative 3 times 4. We do negative 2 times negative 3. And then we add all of those together. 6 minus 12 plus 6, that equals 0. If we're going to find the measure of the angle between P and Q with these measurements, what we're going to do is we're going to make use of this trick that we learned last section, where we can find the dot product and then divide by the magnitude multiplied together of the two vectors, and then we can take the arc cosine to get the angle measurement. So we first find the dot product of P and Q, and we get an answer of negative 11. We then find the magnitude of P. Remember, with these, since we have 3 dimensions, x, y, and z, we have to use all 3 of them while we're doing the calculation. We get the square root of 29 there. And then we do the same thing for Q. We square each one of them and add them together and take the square root of it. And we get the square root of 14. So now we put negative 11 over our two magnitudes multiplied together. So negative 11 over the square root of 29 times the square root of 14. And then we take the arc cosine of that. And if you do, you'll get roughly 123 degrees. Okay, given A is negative 5, 3, and 11, and B is 0, negative 6, and 2, find the dot product and then find the angle between A and B. Well, we can do this. So the dot product, we just multiply x's, y's, z's together, add them together, and we get 4. In order to find the angle between them, remember, we need to make use of the formula that we take the dot product and divide it by the magnitudes of both A and B, and then take the arc cosine of it. So we need to find magnitude of A, which is done that way. We need to find the magnitude of B, which is found there. We then put the original 4, that dot product, over those two square roots being multiplied together, and then we're going to take the arc cosine of that number. And when you do in the calculator, you should get 87.1 degrees. Okay, today the way I want to finish is I want to finish by doing an extended word problem. We're going to see this in example 6, and there's some other problems that actually build on this as well. So we're going to look at this as kind of like a word problem and see how this comes into play. Anyone who's in the airline industry, if anyone who's a pilot, has to be familiar with these kinds of principles. So an airplane taking off at a heading of 180 degrees has an air velocity vector directed 20 degrees above horizontal and an airspeed of 225 knots. There is a 40-knot wind from the southwest. Find the vector that represents the plane's velocity relative to the point of takeoff. So I think the best thing for us to do is first to picture this, so draw it out as cleanly as we can, and then start to try to work through the pieces of it. So here we have a drawing of the plane. So here vector P is the plane that is taking off. Notice that it's at a 20-degree incline that it's taking off from the ground. It's headed, we are told, 180 degrees due south, so we're picturing it that way here. Notice that there is a wind that we're told is coming in this direction at a 45-degree angle. And so this is kind of a depiction of what we've got going on. Now, if we're going to start to solve this problem, we need to, again, get it into its component parts. So in order to do that, we need to figure out how much of the wind is along the x-axis, W1 here, and how much of it is along the y-axis, the W2. In order to do that, we already have the measurement of the angle here of 45 degrees. So we know that we can use cosine of 45 in order to get our x component and sine of 45 to get our y component. So it's just going to be 40, which is the wind speed, 40, times cosine 45, and then 40 sine 45. And notice that the z component is 0 because the wind is not pushing up or down. It's parallel to the ground, so it's along this plane. So there is no z component to the wind. And when you multiply those together, you get 28.3 knots of wind in both the x and then the y direction. All right, so now we want to find the p components, the components for the plane. Notice we need to first find the y. This is going to have a y component and a z component. Notice what it doesn't have is an x component. There's no x component for this, so that's why we have a 0 for the x. And then we're just notating here that in the y direction, it should be a negative value. So it's negative p cosine 20 degrees. Here's our angle. And then sine 20 degrees will give us our p3. And so when we multiply 225 times cosine 20, or negative 225 times cosine 20, we get negative 211.4. And for the other guy, we get 77. All right, so now we have all of the components. So we have the wind components, 28.3, 28.30, and the plane components are 0, negative 211.4, and 77.0. So now we just want to add these together to see what's happening actually to the plane while it's in the air. So we add all those components together, which just means we add the 28.3 plus 0. We're going to add this 28.3 to this negative 211.4, and we're going to add the 0 to the 77. And when we do that, we get 28.3, negative 183.1, and 77. And as I've shown here in the slide, the plane then is actually traveling in this direction because of the wind's influence on the plane as it's taking off. Now, on page 308, exercise 38, we can ask, what is the plane's resultant ground speed? The resultant ground speed. Well, we have the resultant of 28.3, negative 183.1, 77. Now, that's the vector, but the resultant ground speed is a scalar quantity. So what we need to know for that is just, we want to know the magnitude of r. And to find the magnitude of r, we just take the square root of the sum of the squares of each individual component. So here's the x, here's the y, here's the z. We square each of those, we add them together, and we take the square root. And we get around 200.6 knots. This makes sense, right? The plane is being slowed down slightly by the wind that's blowing against the plane. Now it asks, at what bearing is the plane traveling during its takeoff? So remember, bearing is its direction northeast, southwest. Where is it on in a direction, this direction, not the z component? We just want to know on the xy plane where its bearing is. So to get at that, we know that that the r of the x and the y, because we don't care about the z at this point, just the xy, is 28.3 and negative 183.1. So we've just removed the z component from this because we're only looking at it in the xy plane. And so it's kind of easier to draw if we just draw it in a 2D here rather than the 3. So if we're looking at xy, this is just the northeast, southwest. Remember, this is our y and this is our x. Then we can just draw it here. This is the resultant vector, 28.3 and negative 183.1. And we can just use arctangent here, right? Because tangent is opposite over adjacent. So tangent of alpha would be negative 183.1 over 28.3. We take the arctangent of that, or tangent to the negative 1, the inverse tangent, and we get a measurement of negative 81 degrees. So that means if we're looking at compass bearings, remember, we always do compass bearings from due north is 0. Remember, with everything else, we usually think about 0 being over here, but not with compass bearings. Compass bearings, we say that north is 0, and so we need to take that that measurement of 81 and add it to 90 degrees. We need 90 plus 81, and we get the total bearing of 171 degrees. For exercise 40, it asks, what is the plane's resultant angle of inclination to the nearest degree? Okay, so in order to figure that out, remember, we're asking now how much is it going up as it's traveling. In order to do that, we need to first of all come back to what our resultant for the airspeed was to start, which was 200.6. And then we're going to look just in the xy direction, and we're going to figure out how much of that is in the xy. And we find that's 185.3. And now, we now have the xy amount. We now have the total. We have the hypotenuse. So we can actually use arc cosine to solve this for theta. We take the leg. This would be the adjacent, 185.3. We divide it by the hypotenuse, which would be 200.6. And then we take the inverse cosine of that answer. And we get an angle of 23 degrees. And that's the answer. All right, so your homework for 6.3 is going to be page 307 to 308, numbers 2 through 30, and then 42 through 48. Just doing, again, I keep forgetting to write this, doing the evens. So you're doing evens only on those numbers. So 2 through 30, 42 through 48 evens should give you some good practice using all these properties just in 3 dimensions for vectors. All right. Hope it goes well. Let me know if you guys have any problems.